Alright, so I promised conceptual chemistry that I would show them how to solve an example of this problem. So that's the video we're going to do now. This is a situation where you're going to be solving a problem to determine its chemical equation, as well as using the law of conservation to figure out how much reactant or product you have based on other amounts. So we're going to start off. Here's our equation. We have solid glucose. Okay. Here's our formula for glucose. So they tell us it's a solid. This is the name of the substance written out. And then this is the actual formula in the parentheses. That reacts with water. Now they didn't tell us the formula for water because that's one of the formulas we're supposed to know. To yield carbon dioxide, again, a formula we're supposed to know. So to yield, yield by the way means to produce. So they're producing carbon dioxide and oxygen gas. So we want to write the chemical equation for this. To do that, the first thing we want to do is identify what is a reactant and what is a product. Whenever we do a chemical reaction, we have an arrow in the middle that shows the direction of the reaction, and you always start off with your reactants and you make your products. So a typical reaction is going to go left to right, reactants to products. Okay? So if I read through this, it says solid glucose reacts with water. So this word here, reacts, is telling us that these two substances, solid glucose and water, are the reactants. So we're going to add those formulas on the left-hand side of our equation because that's where we put the reactants. So my first substance is solid glucose. So that would be the formula. We don't write the word, we write the formula. So C6H12O6. The other thing we need to tell here is we need to tell what state of matter this is in, what phase. So in this case, we have glucose, and they told us it's solid. So down here, we put a little S with the parentheses. That tells us it's a solid. Now it reacts with water. So we put a plus to show that it's combining with or reacting with this other substance. And we want water. The formula for water that we need to know is H2O. So the question is this a solid, a liquid, or a gas? Well, typically in the equation, if they tell you it's ice, it's going to be a solid. If they tell you it's water, it's going to be a liquid. And if they tell you it's water vapor, it'll be a gas. So in this case, it just says water. So we're going to say it's a liquid. So I put a little L inside of a parentheses. If I continue on my little problem here, so I've essentially got the glucose in there. I'm going to check that off. I've got the water in my equation, so I'm going to check that off. Right? Now it says to yield. Well, yield again, that means produce. So that means that what I'm yielding or producing is going to go on the right side of my equation, the section that's for products. So I look at my first substance, carbon dioxide. The formula for carbon dioxide is CO2. It's a carbon and two oxygens. Okay. So that CO2 I'm then going to put down here. CO2. Now it doesn't say what phase that's in either. It doesn't tell us what state of matter it's in. But carbon dioxide, I know at room temperature is a gas. So we're going to say it's a gas because I'm going to assume this took place at room temp or close to it. So it says to yield carbon dioxide, we've got that, and oxygen gas. Okay, so I put plus and an O. Now there's a problem here. Carbon dioxide, that's a compound, so it's a gas. I can figure out the formula. Oxygen gas is a special type of gas. It is what we call a diatomic. All diatomics, when they are by themselves, meaning in this case oxygen isn't a compound, it's not being combined with any other element, it's just pure oxygen. Anytime you have a pure diatomic, it travels as a pair. So that means that there are two oxygen atoms that are bonded together there, making oxygen gas. I put my little G in parentheses to show it's a gas. That's my equation, that's my answer for this first question. Okay, I've got my states of matter, I've got my formulas, and I've got my arrow in between, my pluses between my reactants, my plus signs between my products. Now, the question that branches off of this, or the next question that you can ask after you come up with this equation, is we can go to the law of conservation of matter. So again, it's the law of conservation. And what the law of conservation says is that the amount of my reactants, the mass, the amount of matter in my reactants must always be equal to the amount of mass in my products. They have to add up to the same number. So to solve this, what I do is I start reading through. It says if 50 grams of water are used. So I go back to my equation up here, and what I do is I write the amount, in this case 50 grams, directly underneath the substance. And if you excuse me, I'm going to erase law of conservation so I have a little bit more room here. Okay, so I put my 50 grams right underneath the substance it belongs to, 50 grams of water. Then I have 60 grams of carbon dioxide. So I find carbon dioxide and I write 60 grams right underneath it. Okay, then I go on, keep reading, and it says 35 grams of oxygen. So I go over to oxygen and I write the 35 grams right underneath oxygen. Those are produced. Then it says how much glucose reacted. So the question is about glucose. Another way of thinking of it, glucose is our unknown. That's what we want to know about. So in algebra, we'd call that the x, right? That's the unknown that we want to solve for. At this point, I have my three masses recorded. I have my x, my unknown that I want to solve for. The last thing I do is I go up here, and anywhere there's a plus, I'm going to bring it down. So a plus and a plus. And then where the arrow is, I'm going to put an equal sign here. What I've done now is I've created an algebra problem. X plus 50 grams equals 60 grams plus 35 grams. We know that everything on this side must equal everything added up on this side. So all I do at this point is I solve for it. So if I take this side, it's X plus 50 grams equals, I'm going to add these two together, so 60 plus 35. Okay, so 60 plus 35, that's going to equal 95 grams. Now to solve for x, I simply subtract 50 from this side, subtract 50 from this side, okay, and that's going to give us x equals 95 minus 50, which gives us 45 grams. That's our answer. So we have reacted 45 grams of glucose. Okay, that's the basic idea. The last thing I want to talk about is, okay, let's say they have 45 grams, but let's say that you want to change that. Let's say that 45 grams is not the unit that we want. Okay, let's say for some reason we need it in kilograms. So how do we convert that? Well, that goes back to last unit. We talked about dimensional analysis. Okay, grams is essentially our base unit in this case. So if we think about it, we go back to the idea of kbm, right? Well, the B in this case is our grams, okay? And we are at G right now. We want to get to K. So for dimensional analysis, the first step is always to write down what's given, 45 grams. We do a dot and a line. The dot is your multiplication sign. The line is going to be our conversion factor. Okay. Now we want to get rid of units of grams, so we're going to put grams on the bottom because we want those to cancel out. If we get rid of grams, we can go one step over and we can convert to kilos. In this case, it's kilograms because we're dealing with mass. Then we need to plug in our numbers. So we know that grams are going to cancel out at this point. We're going to end up with kilograms, so we're good to plug in numbers. We know that for every 1 kilogram, that's going to equal 1,000 grams. So it's 1 kilo equals 1,000 grams. Another way of thinking of this is that kilos are bigger than grams, and we know that this is going to be 1,000 is going to get plugged in here somewhere. So if kilos are bigger, it's going to take a lot of grams to equal a kilo. Okay, so to solve this now, all we're doing, since 1,000 is on the bottom, that means we're dividing. So we simply take 45 divided by 1,000. Okay, now to think of this, to simplify it, think of it as 45 divided by 1,000. That's going to get smaller, right? So that means our decimal, which is right here, needs to go to the left because it's going to get smaller. Then we count up these zeros. We have 1, 2, 3 zeros. So that means our decimal needs to move 1, 2, 3 spots to the left. So that's going to give us 0.045 kilograms. Okay? You got to be careful about these guys though. When you start bouncing this decimal around, it's very easy to miscount. It's also very easy to miscount your zeros, so make sure you plug them in. Okay? And you draw that little decimal so you know that it's got to be right there and there's 1 0. Okay? The last little thing we could do with this is, let's say we don't like this number in particular, we don't like having 0.045, we can put it in scientific notation. So we can take 0.045 kilograms, okay? And scientific notation is all about having one non-zero, so a number other than 0 in front of the decimal. Well, if the decimal is right here, okay, that means that we really want the decimal to go right 2 spots. We want to put the decimal right there. Okay? So in other words, we want our number to be 4.5. Okay? But we need to represent the fact that we have moved that decimal over. So that's where the times 10 to an exponent comes in. This represents the fact that we've moved the decimal over. We moved it 2 spots over, so our exponent is going to be 2. We moved it 1, 2 spots, right? And the last little step is, if this was a decimal, in which case it is, right? It's less than 1. In order to move the decimal over to the right, we were essentially dividing by 10 each time. Okay, so we're doing divide by 10, divide by 10. Dividing by 10 is a negative exponent. Another way of thinking of it is, this number is less than 1, the number that you're converting. If it's less than 1, it will be negative. Okay, so think of like less than 1, negative, right? Greater than 1, positive. Or if you think of it as positive is bigger than negative, okay? So if it's bigger than 1, it's positive. If it's less than 1, it's negative, right? And last but not least, we never have naked numbers. So we go over here and we add our kilograms. The kilograms goes on the outside. It doesn't go in here, okay? It's on the outside because this times 10 to the negative 2 is part of the number, right? That's how you solve it. Okay, look over this, practice it, make sure that you can do it on your practice problems and your review for the test, and you should be good to go.